Right now, tech companies are fighting a massive bidding war over NVIDIA's highest AI chips, like the H100 and the new B100. The demand for this computing power is outstripping the supply at a scale we've never seen before. The true constraint limiting the AI boom is not manufacturing raw silicon. The actual bottleneck is the industry's capacity to physically package those chips. To understand why, we have to look back to 1957. When Fairchild Semiconductor started commercializing the transistor, they had a very basic problem. Airborne dust kept ruining their primitive components. Their solution was to seal the transistors inside metal cans that mimicked old vacuum tubes. Packaging started as a simple dust cover, but as computing scaled up, a physical tension emerged. To connect chips to boards, engineers used long, fragile wires. They took up valuable space. And at high processing speeds, long wires generate electrical interference, inductance, and capacitance that slows data signals down. The protective physical box became the primary barrier to making computers faster. This kicked off a decades-long engineering war against physical space. By the 1960s and 70s, the dominant standard was the DIP, or dual inline package. It was a rectangular block with 2 rows of pins sticking out. To install it, you had to physically drill holes straight through the green motherboard. Because of the size and the drilling, engineers were limited in how many components they could pack into one space. Then the consumer electronics boom hit. Devices like the Sony Walkman forced engineers to find a way to shrink their designs to fit inside a pocket. Drilling holes through the board was taking up too much room. The breakthrough was surface mount technology, or SMT. Instead of drilling, engineers shrank the pins and glued the components directly onto the surface of the printed circuit board. By using both the front and the back, component density instantly doubled. At the time, American and Japanese tech giants looked at this new assembly process and saw low-margin, blue-collar labor. They outsourced the entire packaging process to emerging companies in South Korea and Taiwan to keep their own overhead low. By offloading what they considered a low-margin afterthought, Western manufacturers inadvertently concentrated the industry's most critical engineering bottleneck in the same factories they went to for cheap labor. In the 1980s, the PC boom introduced a new spatial bottleneck. Intel was transitioning to 32-bit processors. To handle that much data, the new chips required 132 individual connection pins. There simply wasn't enough physical room around the outer perimeter of a flat chip to fit them all. To solve this, engineers abandoned the edges entirely. They developed the ball grid array, or BGA. Instead of a perimeter of pins, they placed a dense grid of tiny metal solder balls across the entire bottom surface area of the chip. Then came an even more radical leap. They physically flipped the bare silicon chip upside down. By placing the active processing side directly against the packaging substrate, they entirely eliminated the need for internal wire bonds. Every single time the tech industry hit a horizontal physical wall, engineers survived by exploiting hidden vertical space. That changed exactly how data exits the processor. By the 2010s, extreme miniaturization presented a new challenge. Apple's leadership wanted to fit an entire smartphone's worth of processing power inside a wristwatch. The problem was that even the most advanced, highly shrunken motherboards were physically too large to fit inside that tiny casing. The packaging firm ASE took on the order and executed a radical solution. They eliminated the traditional green fiberglass motherboard completely. They built a system-in-package, or SiP. Instead of wiring separate parts to a board, they embedded the processor, the memory, the sensors, and the power management together into one unified solid block. This shift turned packaging into the system itself, fusing every component into a unified block to defeat the physical constraints of the motherboard. Today, we face the ultimate bottleneck, the death of Moore's law. As engineers shrink individual transistors down to their atomic limits, cramming more of them onto a single chip no longer yields the same massive speed gains. TSMC realized that to keep increasing computing speed, they had to stitch multiple separate chips together. But they needed a level of microscopic precision that traditional plastic packaging firms simply couldn't achieve. TSMC's breakthrough technology is called CoWoS. Instead of resting chips on standard plastic or fiberglass, CoWoS uses a silicon interposer. It acts as a microscopic silicon superhighway to connect chips side by side with immense bandwidth. This brings us back to the artificial intelligence boom. Modern AI requires moving massive amounts of data instantly. This is possible because CoWoS allows GPUs and memory to sit together on this silicon superhighway. Now the frontier is moving. The industry is shifting from 2D arrangements to stacking logic and memory vertically, like 3D skyscrapers wired directly through the silicon. The trillion-dollar struggle for AI dominance now happens inside the package. The metal can originally built to block dust has become the defining architecture of modern computing.